Hello everyone, I'm Richard Li, a graduate student from the Hong Kong University of Science and Technology Guangzhou. I'm pleased to introduce our work today, a deep cybersickness predictor through kinematic data with encoded physiological representation. If you have ever experienced VR devices, it's likely that you have encountered cybersickness. The symptoms include headache and disorientation. Researchers have proposed theories to explain this phenomenon. The sensory conflict theory suggests that when you are in a VR experience, your eyes tell that you are in motion, while your inner ear sensors tell you that you are still. The conflict between these two sensory inputs leads to cybersickness. Other theories include the postural instability theory and the subjective vertigo theory. Typically, cybersickness can be assessed through subjective and objective measures. Subjective measures often involve questionnaires where participants rate their discomfort on a scale. Objective measures may include physiological signals, with severe cybersickness often accompanied by a significant fluctuation. Therefore, it's important to predict the onset of cybersickness during virtual navigation. On one hand, previous researches rely on data from integrated sensors such as video data. However, these data struggle to reflect individual difference. On the other hand, some studies have used physiological signal data, but these require additional physiological sensors and can limit users' mobility and interaction. To overcome these limitations, the prediction method should be less intrusive and cognitive effortless, while considering individual differences during interaction. So, how do we design such a prediction method? Here is an overview of the methodology. First, the data collection. Next, data processing. Following that is an introduction to the model architecture. Finally, there are some experiments conducted under different parameter settings. In the user study, a total of 53 participants were involved. After an instruction session and the completion of the first SSQ questionnaire, participants put on VR devices and navigated through the virtual environment following the highlighted route. After a 4 minutes immersion, they completed the SSQ questionnaire for the second time. The difference between the two questionnaires were used as ground truth for the severity of cybersickness. For each experiment, we collected head tracking data, including head position and head rotation, motion data, and physiological data. After obtaining the data, we first defined the ground truth using three values, 5, 20, and 14. We divided the samples into 4 categories. In practical application, we aim to predict the level of cybersickness using the historical data. Therefore, the program definition involves utilizing historical data, while dt represents the data collected at time t. This data includes 4 data points from electrothermal activity, as the EDA is sampled at a frequency of 4 Hz. To further increase the sample size, we divide the original 4-minute data into multiple segments using different time span. For example, with a time span of 30 seconds, the sample size can be increased by a factor of 8, and the problem becomes prediction based on data from the first to 30 seconds, then from 31 to 60 seconds, and so on. The first model is based on electrothermal activity data. The raw EDA data is decomposed to obtain horizontal signal (HCl) and the transient signal (SCR). These components form the time series feature of the EDA data. Additionally, other features such as mean, variance, and more, totaling 38 dimensions, constitute the numerical features of the EDA signal. The time series features are processed using long short-term memory networks, while the numerical features are handled by feed-forward neural networks. These two types of features are combined to create a representation of the physiological signal, which is further used for prediction. It's worth noting that this physiological representation will be used as a part of subsequent models. The kinematic model utilizes kinematic data, including head tracking and motion data. A total of 16 dimensions of time series features are extracted and directly inputs into a feed-forward neural network for prediction. Of particular importance is our EDA-enhanced kinematic model. It relies only on the inputs of the kinematic features, thus requiring only the sensors integrated into the head-mounted displays. Additionally, it learns a mapping from kinematic features to physiological embedding, which is achieved through LSTM and feed-forward neural networks. During training, the mean squared error between the physiological embedding and the physiological representation, which is learned from the EDA model, is added into the loss function. On the other hand, the model also learns kinematic embedding using LSTM and feed-forward neural networks. The kinematic embedding is combined with physiological embedding to predict the level of cybersickness. The close entropy loss between the model's output and the ground truth is also part of the loss function. To show the efficiency of the proposed EDA-enhanced kinematic model, we also built the kinematic EDA fusion model. This model combines EDA features and kinematic features for prediction. The model is composed of LSTM layers and fully connected layers. We identified certain parameters that may have an impact on the experimental results, such as the time span. Different time span settings, including 10 seconds, 15 seconds, 20 seconds, 13 seconds, and 40 seconds, divide the original 4-minute data into 24, 16, 12, 8, and 6 segments respectively. The graph displayed here illustrates the case where the time span is set to 30 seconds, resulting in data being divided into 8 segments. Finally, we found that the EDA-enhanced kinematic model performed the best, slightly outperforming the fusion model, and it showed a noticeable improvement compared to the single modality kinematic model and the EDA model. However, there was a trend of decreasing model performance with an increase in time span, which contradicts our intuition. Intuitively, a larger time span should provide more information and enhance the model's predictive performance. Therefore, we hypothesize that the size of training dataset may be a bottleneck for the model performance. To validate this idea, we conducted random upsampling to ensure consistency in the size of the training dataset. After conducting experiments with these adjustments, we found that the EDA-enhanced kinematic model still achieved the best performance. Moreover, the model's performance improved as the time span increased, indicating that longer time span indeed contain more information for prediction. In order to find a trade-off between the number of training samples and the amount of information carried, we plotted the performance curve. We observed a turning point in 3 of these curves at a time span of 20 seconds. Therefore, we consider 20 seconds to be a balanced value that strikes a trade-off between training sample size and the information content. Additionally, we conducted experiments to verify the relationship between exposure time and model performance. We truncated the 4 minutes time and removed the initial data. Truncating the first n time segments, each 20 seconds long, yields data ranging from the n plus 20 seconds to 1240 seconds. After retraining the kinematic model and the EDA model, we observed a strong correlation between exposure time and model performance for the kinematic model, while this correlation was weak for the EDA model, possibly due to the noise in the physiological signals. In summary, we believe that users are likely to experience a low cybersickness level at the beginning of the exposure, with the cybersickness level gradually increase as the exposure time lengthens. In conclusion, this article presents several prediction models for different data modalities. Firstly, the EDA feature extraction significantly improved the predictive performance when using only EDA data. Secondly, the EDA-enhanced kinematic model achieved the highest accuracy of 97.8%. Finally, the EDA-enhanced kinematic model holds substantial practical value as it relies only on the integrated sensors within head-mounted displays. Thank you for your listening. Please feel free to ask any questions.